Science time. Today we are talking about science. So today's science lesson is called Science. Justinian's on the door shutting expedition. There's two, that one too, thank you. Today we're talking about science, and we're going to use the framework of what the Nebraska Science Standards call science and engineering practices and cross-cutting concepts for that. And so the objective is explore SEPs, so I want you to write down this objective, explore SEPs and CCCs. The objective, the verb of the objective is explore, because we're not going to totally exhaust the topic today. We're just going to start our exploration of it. What I want you to think about when you're exploring something is we're not getting into the real nitty-gritty, very, very detailed of science. We're not talking about all of science in this 20-minute discussion. We're just talking about, in general, what science is about. So I would like if someone could define, this is almost always how we just start every discussion, define this main topic. This is the main idea. This is the title. Define would you give him a Jolly Rancher? Just find a Jolly Rancher. There aren't any, so good luck. Maybe... Yeah, there are no Jolly Ranchers in there. Oh, a watermelon gum. The top drawer has watermelon gum. I think that's a good one. Yeah, it'll work. Okay, someone define science for me in your own words.
Thank you, Mr. Kemp.
You're welcome. In your own words, even. If you had your own words from your vocab, what does science mean to you? Yeah, we do. She's done. But I want in your own words. So maybe it's good that she ain't here. You don't have to look. Just say it in your own words. It's okay. You're not gonna. If you're wrong, I'll pretend you're not, and then we'll make it right. It doesn't. It does. You don't. No one has to see your voice, and the mic is here. It's how you're gonna pick up your voice. In the future, you'll look back on this video. You'll be like, "Who was that fool who said that?" No, you're not a fool. Just tell me. Tell me. Tell me. Do it. Justinian. Oh no! Now I've ruined it. Now we all know. Okay. Someone raise your hand. Let's hear it. What do you think science is?
Science is the study of the universe.
Okay, yeah. Study of. I really want to talk about that. And the universe. How could anything not be the study of the universe, right? The whole point of the universe, the uni, is that it's all one. Everything you do is part of the universe. You are part of the universe. You came out of the universe. To the universe you will return. It's all one thing. And so everything you do, in a sense, is studying the universe. But just you learning and growing is studying the universe. But these words, study of, I want to remind you that this is the suffix in science we use, ology. You've heard of biology or geology or other ologies, kinesiology. I don't know, there's lots of them. You've heard that ending before, right? What's another one? Hydrology. There's so many, right? This suffix, study of, we use a lot in the science. And that's a way that human beings categorize the things that we talk about. So science is a way of studying the universe. It is a way, I'm going to suppose this to you, a way of looking at the universe. I'm going to put the world, but that's the same thing. When I say the world, I don't just mean our planet. Although most of our science, especially in this class, will be restricted to that. But it's a way of looking at the world. It's a way of looking at the universe. It's not just memorizing all the facts about something. Okay, that's not science. Science is a thing that you do, not just that you memorize. So you do science. Did you do science this week? Mm-hmm. In fact, you not only did science, not only did you have a certain way of looking at the world and learning about it, but you solved a problem. Right? And that's another thing that we're going to talk about called engineering. Engineering is, so if science is a way of looking at the world, engineering is a way of solving problems. And both of these can be as strictly defined or as narrowly defined or as loosely defined as the situation calls for. So the example I often use is, you've probably seen on the poster on the back, I think it's on the back of this door, it might be on the door to Mr. O's room, but you've seen the steps of scientific method. Ask a question, form a hypothesis, perform an experiment, that kind of thing. You've seen that. You've heard of the steps of the scientific method before. I'm going to propose to you that I like the scientific method that I kind of made up, which is this 3 steps, which is you have some kind of question or problem or statement or something, but you make some kind of observation. Then you perform some kind of research or test. You perform some kind of examination, maybe an exploration, you could say, and then you form a conclusion. So is it science if a new drug is developed that they think will cure headaches in people, and they have to run it through years of clinical trials, first in rats, then in chimpanzees, then in people? Is that science? And they publish a paper about it. Is that science? Of course it is. That's kind of the classic way we think about science. That's the scientific method on the back of Mr. O's door, where there's a problem, people have headaches. There's a hypothesis, maybe this drug will work. And then there's an experiment run, a very, very rigorous, double-blind controlled study that shows whether or not this drug is effective in this % of people, and then there's a scientific paper published about it. Of course that's science. But it's also science if you observe a cute girl across the gym at a away volleyball game, you ask your buddy what's her name, and he tells you it's, I don't know, what's a cute girl name? Monica. Was that Justinian? God bless you. Yeah. So, like you see that's a silly example, but what I'm trying to show to you is that you are a scientist, that you're doing science all the time. Even if it's not in the strictest sense like white lab coat and Keslin's pink goggles science, it's not that kind of science necessarily, but you're doing the method of science all the time when you look at the world with curiosity. And I guess really that's the main thing. If you're being curious about the world, you are doing science. And engineering, similarly, is a way of solving problems. This also can be as narrowly defined as we have to do this math to make a bridge so that it doesn't fall down when people drive over it. That's a very, very high level of engineering. But also, when you're building your dumpy little, and might I add, non-functional egg dropping thing that is supposed to protect an egg, but instead just lets it drop like a rock, like every single group might as well have just dropped the egg plain, you're still finding a way of solving problems. Obviously not a very good way, but you still found a way to solve a problem. The problem was the egg was going to break, and you thought, never mind, I'm just going to let it break. But engineering is a way of solving problems. If you're rearranging furniture with your mom in the living room, and you're like, oh, the TV's going to have a glare if we arrange it in this way, that's engineering. That's a way of solving problems, okay? So science is a way of looking at the world. Engineering is a way of solving problems. And technology, well, what is technology? You tell me. Is it only computers? Only phones? Those are good examples. I appreciate that. TV is an example. How do we think of a definition, though? Okay, sure. Let's say man-made. Now listen, I'm not sexist, but no, I'm just kidding. Man-made meaning human-made, not only males. It's man-made is just a word we use. Man-made artifact, I'm going to put that. Like just, it's a something, it's a thing. Man-made artifact to help solve problems. Is a stick technology. If you're using the stick to lift a boulder, I would say that counts. I mean, you didn't make the stick, but you're using it as an artifact. You made it a lever. The stick existed, and you made it into a lever. Is Facebook a technology? Yeah. Even if you can't touch it, it could still be a technology. Is Senso a technology? You guys love Senso. I love Senso. I'm always muting people's computers on Senso in the background when they're not even in my class. They're like, oh, what happened? My computer got muted. When they're in another class. And they're listening, we don't know. They could be listening to anything. But so these 3 topics, science, engineering, and technology, are the focus of this lesson. And so, as I said, the Nebraska State Standards organize these into SEPs and CCCs. So this is science and engineering practices. See that that's the top poster. For this class, those are probably the 2 most important posters in the room. Besides these ones are great. S is for sharing. You'll find it can be fun. Those ones help you live your lives as better people. But these ones help you do your science. And so science and engineering practices, we have 8 of them. You can see them there. We're going to go through them each. You are doing science or engineering or both when you, 1, ask questions and define problems. Have you ever done that? Have you ever asked a question? Of course you have. Or defined a problem. Mom, the toilet's clogged. That's a kind of science and engineering practice, right? That's defining a problem. My point is, I'm using these dumb little examples because my point is that you are already a scientist and an engineer. You don't get paid to do those things, but you are a scientist when you observe the world, and you are an engineer when you look at ways of solving problems. Another science and engineering practice, develop and use models. What's a model? We're going to talk about this more in the future. What's a model in general? Yeah, not necessarily small. If you think about a model of an atom, that's much bigger. But it's a representation of something that we know has shortcomings, right? Like it might be smaller. We might have a model F-16, and you know it's not going to like fly around and shoot missiles at Russians because it's just a model, right? It's much smaller. We might have a model atom, and we know it's not perfect because it's made out of wood, and atoms seem not to be made out of wood. But so it's a representation of something with imperfections. What about planning and carrying out investigations? What's an investigation? What's an investigation? Yeah, okay, you can test things. Yep. So it's just a way of looking at things. That's again my silly little example about who's that cute, I forget if I said boy or girl, but who's that cute one across the gym? That's an investigation. Like you ask, what's her name? You ask your bud, what's her name? It's obviously Monica. What's her name? That's an investigation. Analyze and interpret data. Well, man, I'm running out of dumb examples. If you sort your Pokemon in Pokemon Go by what type they are, you have analyzed and interpreted data, right? There's a list of things, and you have analyzed, which means you've gone into the details of it, and interpreted, which means made sense of it. Using math and computational thinking. Have you ever used math?
No.
Never. Not once. Not one time. Okay? Constructing explanations and designing solutions. That was your lab. That was your lab, designing solutions. Did you do a good job? No, of course not. You'll do better in the future, I hope. Otherwise, no talkies for you. Engage in an argument from evidence. This one's really important that you know the distinction. I think Mrs. Moreva probably talked about this with you when you did the claim, evidence, reason. You ever remember claim, evidence, reason? That's an argument from evidence. An argument from evidence is not just, or it's not when, like you say, Mom, I'm going out tonight, and she says, no, you ain't, and then you guys have fight about it, and you yell at each other for 15 minutes. That is not the kind of argument we're talking about. An argument from evidence in science is when I have evidence that supports some topic, and there is someone else who has maybe even the same evidence, but they interpret it in a different way. We might have a discussion where we compare our evidence and our conclusions, and that's an argument, but it's not usually with raising voices, although sometimes I'm sure that happens, and it's not usually just yelling at each other. There's actual evidence involved. And then finally, the last SEP is obtaining, evaluating, communicating information. That's the conclusion step. Your friend says, Monica. That is them communicating information to you. Okay? So we have SEPs. There are 8 of them. These are the science and engineering practices. Those will be on that board all year long. Then we have CCCs. These are the cross-cutting concepts. See? SEP. CCC. These are called cross-cutting concepts because they are concepts, that is ideas, that cut across all the kinds of science. Basically, they're ideas that apply to all the kinds of science. What are they? Let's read them aloud. Kai, we're just going to go around the room. Kyson, read the first one on that board there. Yep. Jasper? Ava? I think proportion.
And
Quantity. We'll have Daxton go next. Good. Tally?
energy matter.
Justinian?
I cannot see it.
It's purple.
Structure and function.
Good. And Sri? Good. So those are the ones when your lab form asks you which CCC, or I think it says which cross-cutting concept best applies to your lab or best supports your data or whatever, you pick one of those and then you explain it. Because let me tell you, the fact that they cut across all the kinds of science means they always apply. In every kind of science you can make a case for how it applies. But you're to pick the best one that you think applies the most and explain why it applies so that I know that you understand those. So those are the cross-cutting concepts. So there we have the SEPs and CCs. We're exploring them. Let me tell you, this is the objective that we're not going to meet this objective. We're not going to fully explore these in this lesson. But as we go throughout the year, we're going to explore the SEPs and CCCs. Now, what are the tools that a scientist uses? Well, first of all, we have some, let me change colors here. We have some actual tools. Would you list for me some tools that a scientist uses? Beaker. Let's just list a few more of them. This is for fun. This is fun. I'm having a good time. What are some other tools a scientist uses? Okay. What else? Test tube, yeah. Did you someone say beaker? Okay, we got other beakers. Graduated cylinder. So far, scientists do use glassware. That's absolutely true. Safety goggles, yes. Lab coat. So we have personal protective equipment. These are all beakers. That's not really their main job. Test tube, it's not their job at all. But there are things that we measure with. So can we think of other measuring tools a scientist might use? A ruler, a scale, thermometer, tape measure. Yeah, so scientists measure things. And does anyone know what is the system of units that a scientist uses? I told you, what's that?
Centimeters.
Yes, centimeters is one of them. What is the name of the system? Grams is another one. What's the name of the whole system? Metric is the old name for it, but we now call it the SI, which stands for, in French, the Système, I think these accent marks go like that, International. But it's the new name for the metric. I mean, it's new. It's like 1963, so it's not very new. But it's another name for the metric system. And we use those units, which your review will have you look up on your own. It'll say, like, what does a scientist use to measure length and things like that. And so you'll look those up. And then another tool, not in the physical sense, but another tool, I'm going to shift colors again, that a scientist uses, where should I put this? Down here. Experimentation. What is an experiment? Yeah, when we test, I'm going to define it this way. Testing one thing, I'm just going to put thing. I don't love to put that when we're defining stuff, but testing one thing against another thing. So we're testing one thing called an independent variable. Have you ever heard of that before? What's the independent variable? Yeah, something that the experimenter manipulates, what the scientist manipulates in the experiment. So if you have the very classic example of experiment of where does a plant grow best? In the sunlight or in the shadow, in the closet? You did this in 7th grade science, I think, right? Did you? Mr. O used to have 7th graders, like, you get a bean and you plant it and it grows in the sun and another one grows in the closet. Well, okay, let's pretend you did do that. Do you understand where I'm going with it, though? So what's the independent variable? What did the experimenter change? Yeah, the amount of light, or the light source, how much light it's getting. And you're measuring it against another thing. What are you going to measure about it? The dependent variable, yeah, you're going to measure its growth. The dependent variable is measured. So the independent variable is changed, like the experimenter changes that, and the dependent variable is what you measure. In every lab that you do, you will need to have these variables, and you'll need to write them in your conclusion, what you changed and what you measured about that change. The independent and dependent variables. Now you can only, in most methods, you can only have one thing that you're changing. What do you call all the other stuff that stays the same? Does anyone know? Constants. Constants, like if something is constant, it stays the same. Constants stay the same. So what in that experiment will we want to keep the same? The point of a constant is so that we know that the thing we measure actually was because of the thing we changed. What in that experiment would we want to keep the same?
on how much you water it.
Yeah, give them the same amount of water, right? Because if you give one twice the water and it's in the dark, well, how do you know if its growth was because of the water or because of the dark? Okay, so what else would we want to say the same for that experiment?
The nutrients in the soil.
Yep, this kind of soil it has, how many nutrients in it, probably the temperature, right? The air pressure, all those things that could affect a plant, but we want to make sure they don't, and so we keep them the same, are called constants. Okay, questions about the way that we you do experiments in science. And this is important for you because, like I said, 90% of this class I want you to learn from what you're doing in the lab, and you're going to be doing these. And I want it to be an experiment with an independent variable and a dependent variable. You have questions about that experiment, that tool of science that is experimentation. So as I said before, there's a kind of science where you're just asking your buddy what that cute girl's name is. But there's also the kind we want to do in the lab, which is primarily experimentation, controlled experiments of how one thing affects another. Questions about experimentation? Questions about science, engineering, technology, SCPs, or CCCs? You know where to find the SCPs and CCCs? Okay, if you have questions about those, let me know. Justine, are you raising? Oh, you just pointing. Does this track with what you've heard of science and engineering and technology in the past? Okay. Let me make sure that I've got everything here. Oh, hypothesis. What's true of a hypothesis? We talked about this when we were doing your lab. But what has to be true of a hypothesis? It has to be what? What does a hypothesis have to be? Look on your lab form. It's on there. It has to relate to your objective in this class, but that's just so that you're on track for doing the right thing. What else does it have to be? Disprovable. You have to be able to think of a way that this might be proven wrong. So if the hypothesis is turkeys are the coolest animal, is that a hypothesis? No, because you can't. There's no way you could disprove that. Like if Jasper says, I don't know why he ever would, but he says turkeys are the coolest animal, you can't prove him wrong. That's just his opinion, right? If someone says God created the universe, you can't disprove that, and so it's not a scientific hypothesis. Whether that's true or not, it isn't part of science, and so that's just outside the realm of science. Not good or bad, just outside the realm of science, okay? Same thing with like, I saw a ghost last night. Well, that's not a scientific hypothesis. Whether it's true or not is not what we're talking about, but it's not scientifically disprovable, and so it doesn't count as a scientific hypothesis. So what I'm trying to get at is there are things that are outside of science, and it's fine. That's not like those things are worse. They're just not within the realm of science. So science is concerned with things that are disprovable. There's lots of stuff, at least in my opinion, in the universe, that everything is one, that can't be proven or disproven. That doesn't mean it's real or fake or bad or good. It just means it can't be disproven, and so it's not within science. We'll talk a lot more about that as the year goes on, but do you have questions about any of that as we finish up here?